Now, I'd like to talk about something which is a little bit counterintuitive. I think it's really a question. Do you actually learn anything by measuring the same system twice? The conventional answer would probably be no, because let's look at the following scenario. So suppose I have some input state here, a qubit in an input state, and I'll call it psi in. And what's going to happen is this is my qubit, and then Alice is going to measure say sigma z. Now sigma z has two eigenstates, 0 and 1. So when Alice measures sigma z, she's either going to get 0 or 1. So one possibility is she gets 0, and the other possibility is she gets 1. Now, suppose the qubit is then going to be passed on to somebody else, who we'll call Bob. Now, does Bob learn anything by measuring the qubit that Alice passes along to him about the input state? And you might think the answer is no, because Alice, by measuring sigma z, it kind of looks like she destroyed the information about the initial state. Since everything, she's only going to get a 0 or a 1. That's all she could possibly get. And so the only information Bob is going to get is whether Alice got a 0 or a 1. So does that really tell him much of anything about the input state? Well, surprisingly enough, it can. And let me give you a scenario which is a little bit different. So let's make it even worse for Bob. So the first part is the same. So here's our qubit. It's in the state psi n. It's going to go to Alice. And what's going to happen is that Alice isn't going to measure in sigma z. She's going to measure in some totally unknown basis that Bob has no idea what it is. So Alice measures. And then she takes her qubit and she passes it along to Bob. So this really looks pretty hopeless. I mean, in this case, Bob perhaps knew that Alice was measuring sigma z. So by getting the result from Alice, then he at least knew what she was measuring, and he could probably make some kind of correlation between Alice's measurement and the input qubit. But now Alice is measuring some totally unknown basis. Bob has no idea what it is. So it really seems like in this case, Alice's measurement is just going to totally wreck the input state, and poor Bob is not going to learn anything by measuring the qubit again. So let's take a look at this in a little bit more detail. So Alice is going to measure an unknown basis. So what is that basis going to be? So let me write it down. So I have to specify it by two angles. I'm going to so this is Alice's basis, Alice's measurement basis. So I'm going to have two perpendicular states, psi, theta, and phi, equals. So it's going to be cosine theta over 2, 0. Now let's put it down here, plus e to the I phi times sine theta over 2, 1. And the second part of the basis has to be orthogonal to the first. Okay, that is equal to minus sine theta over 2, 0, plus e to the I phi cosine theta over 2, 1. So Alice is going to measure in that basis, and then Bob is going to try to figure out something about the input state. So let's see what Bob's state looks like. So the point is that since Bob has no idea what theta and phi are. He's going, in order to find out what kind of a state Bob gets, we're going to have to average over the angles because Bob has no idea what they are. And the thetas are all equally likely and the phis are all equally likely. So when Bob gets his qubit, it's going to get some state, and to figure that state, we're going to have to average over the angles. Now, let's actually do the average over the angles that I said we're going to do, because again, just a reminder, Alice measured in this basis. Bob has no idea what theta and phi are, and we're going to assume that they're all equally likely. So what does Bob's state actually look like? Well, Alice got psi in, and she could either get psi theta phi, or she could get psi perp theta phi. The probability that she gets psi theta phi is just given by this inner product of psi in with psi theta phi squared. And if she gets that result, what will be transmitted to Bob is psi theta phi, because that's what her qubit will be in after she measures in this basis and gets that result. So the first term here is what happens if Alice gets psi theta phi. The second term is just what happens if Alice gets psi perp theta phi. So the probability that she gets psi perp theta phi is just this thing squared, inner product of psi in with psi perp theta phi squared. And if she gets that result, then the qubit going on to Bob is in this state. So Bob's state is described by this density matrix. And then it's just a matter of plugging this in here, doing a bunch of integrals, and I'm going to spare you all of that and just give you the answer, because the actual answer is pretty simple. What you get is that this is simply equal to 1/3 times sine n plus 1/3 times the identity. So let's discuss what that means. So first of all, the fact that psi n is there tells you that information about psi n is still in the state. Okay, so row B contains information about psi n. And the fact that Alice has measured in a totally unknown basis and then passed the qubit to Bob doesn't destroy all the information about psi n. What Bob gets is basically a noisy version of psi n. And by measuring that state, he can, in principle, get some information about psi n. Certainly not as much as Alice got, because Alice just started with the psi n without all this other stuff. But Bob now gets a noisy version of psi n as a result of Alice's measurement. So having Alice measure the state and Bob measure the state, both of them can get information about the original input state. So it actually pays, in this case, to measure the same system twice, even though it's generally said in typical quantum courses that when you make a measurement, you destroy all the information about what you're measuring. Not necessarily. So this is one particular case where measuring the same system twice is useful. What I'm going to go into next is I need to talk a little bit about a procedure called unambiguous state discrimination. And I'm going to first give you kind of a baby version of it, which gives you the idea of how it works. And then I will discuss without detail a more sophisticated version and show, in that case, how doing unambiguous state discrimination twice in a row can allow two people to get perfect information out of a state. And the first information does not necessarily destroy all the information, and the second person measuring can get additional information.